Hello students and welcome to my channel Maths-Part. So in this video, I will be focusing on matrices and the topic would be canonical form. So in the previous video, if you have gone through, it was focusing on quadratic form. So how from a quadratic form we reduce it to a canonical form, that I'll explain it to you, right? So if you haven't watched the previous video, do watch it and get to know what is a quadratic form. So now, just to revise, a quadratic form is a homogeneous polynomial of degree 2 in n variables, right? So if we restrict it to 3 variables, the quadratic form would be ax squared plus by squared plus cz squared plus 2fyz plus 2gzx plus 2hxy. And in the last video, I also told you that how we convert this quadratic form into a matrix notation. So this is how we convert it into a matrix notation. We place the diagonal positions A, B, C, and then depending upon the positions, we take the half of the coefficients and we place it at those positions, right? Now, how to convert this quadratic form to a canonical form? In a canonical form, what we do, we first from the quadratic form, we will try to convert it into a matrix notation from the quadratic form. We will convert it into a matrix notation. That means we'll convert it into a matrix A. And after converting into a matrix A, we will calculate the eigenvalues corresponding to that matrix, right? Then corresponding to every eigenvalue, we will have the eigenvector, that is x1, x2 and x3. And then we will frame the modal matrix P by placing the eigenvectors along the columns, like we do in the diagonalization process. So do watch my video on diagonalization. So we will get the modal matrix P, and once I get the modal matrix P, we will calculate its inverse and we will try to establish the product of P inverse AP. And when we calculate P inverse AP, we will get a diagonal matrix. And what happens in the diagonal matrix is that we get all the eigenvalues placed in the diagonal positions and rest all the elements become 0. All the non-diagonal elements become 0. So this is what is a canonical form. That means in the canonical form, we only need the positions of diagonals. Rest all the positions should be converted to 0. Right? So in this case, after getting the modal matrix P, we will write P inverse AP and we will get the diagonal matrix, or which is also known as the spectral matrix. So a quadratic form can be reduced to a canonical form using the concept of diagonalization. So sometimes instead of canonical form, we also say that it is sum of square forms, right? Because you only get elements along the diagonals, right? So you can see that when you have the matrix converted in the diagonal form, you will get lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, lambda 3. So if I convert it into a polynomial expression, if I have these positions as x, y, z, what will happen? Lambda 1 will be the coefficient of x square, lambda 2 will be the coefficient of y square, and lambda 3 will be the coefficient of z square. So when you convert this into a polynomial expression, you will get lambda 1 x square, lambda 2 y square plus lambda 3 z square. So isn't this sum of squares? So this is what is exactly a canonical form. So what is the difference between a quadratic form and a canonical form? In a quadratic form, you have mixed terms x, y, y, z, z, x. But in a canonical form, you only have pure terms. It will be only x square, y square and z square. Rest all the terms will become 0. Right? So now the question is, from a quadratic form, how you reduce it to a canonical form. This is the same as we did in the diagonalization process. Right? So now, what are the terms index and signature corresponding to a canonical form? Now the index refers to the number of positive terms in the canonical form. So if I'm writing a canonical form as lambda 1 x squared plus lambda 2 y squared plus lambda 3 z squared. So the terms means these terms, the eigenvalues that we are getting. If they are all positive, then it is called as index. And what is signature? Signature is the difference of the positive and the negative terms. That means whatever eigenvalues you are getting, segregate the positive eigenvalues and segregate the negative eigenvalues. Take the difference and you get the signature, right? So now let us try to calculate this. Find the nature, index and signature of this quadratic form, right? So first of all, for this quadratic form, we have to calculate the eigenvalues. So let us convert this quadratic form into a matrix notation. So you can see that all the diagonal positions are 0. And now we have x1, x2, x3 variables. So let us put these places as x1, x2 and x3. Similarly, this is x1, this is x2 and this is x3. So we are given x1 to x1, x2 means this position and this position. So it is 2. So we will place 1, 1 here. Then we have 2 x1, x3. So x1 and x3, 1, 1 again here. And x2, x3. So it is 1 and 1 again here. Right? Now for this matrix, let us convert it into, let us check what are the eigenvalues, right? So let us convert A minus lambda I matrix. And for that, we will again use that shortcut lambda cube minus trace. What is the trace? It is 0 only. 0 into lambda square plus sum of the minors along the diagonals. So what is the minor along 0? It is 0 minus 1. So we get minus 1. Then the diagonal along this 0 is again 0 minus 1. So it is minus 1 again. So I can write here minus 1. And the diagonal along the third diagonal is again 0 minus 1. So it is minus 1 into lambda. Minus, what is the determinant? 0 into everything is 0. So minus 1 into 0 minus 1. And then we have plus 1 into 1 minus 0. So it is 1. So we get 1 plus 1, that is 2. Right? So this is your coefficient matrix. Now if this is the coefficient matrix, let us put it equal to 0. So we get basically lambda cube minus 3 lambda minus 2 is equal to 0. Clear? So now let us try to calculate one of the root using the hit and trial method. So let us put lambda equal to minus 1. So minus 1 cube minus 3 into minus 1 minus 2. So this is minus 1, this is plus 3, this is minus 2. So it is becoming 0. So lambda equal to 1 is one of the roots of this equation, right? So if lambda equal to 1 is one of the roots of this equation, so let us try to calculate the other two roots. So let us put minus 1 over here. The coefficient of lambda cube is 1. The coefficient of lambda square is missing. The coefficient of lambda is minus 3. And the coefficient of the constant term is minus 2. Let us place this 1 here. Minus 1 into 1 is minus 1. Add minus 1. Minus 1 into minus 1 is 1. Add minus 2. Minus 1 into minus 2 is 2. Add, you will get a 0 over here. So the quadratic expression that we obtain is lambda square minus lambda minus 2 lambda is equal to 0. Let us solve this equation by middle term splitting. This is lambda square minus 2 lambda plus lambda minus 2 lambda is equal to 0. Sorry, I have missed one term. Lambda square, yes, this is minus 2, isn't it? Yeah. So now from here, I can take out lambda common plus 1 into lambda minus 2. So my roots are basically minus 1, 2 and minus 1. Right? Now, for minus 1, 2 and minus 1, if I check, so these are my eigenvalues, right? So if I try to diagonalize this matrix, I will get the entries minus 1, 0, 0, 0, 2, 0 and 0, 0, minus 1. Right? Now, these are my diagonal positions. Now, let us check what is the nature. So, if I check the nature, I can see one eigenvalue is positive, the other two eigenvalues are negative. So, what is the nature according to the previous concept, the previous video? It is indefinite, isn't it? Now, what is the index? How many positive eigenvalues are we getting? 1. So, the index is equal to 1. And what is the signature? The signature is number of positive minus number of negative terms. So number of positive term is 1, number of negative terms is 2. So my answer is, signature is right. So I hope it is clear, right? Okay. So try this question as an exercise and do let me know what are the answers you are getting as the nature index and signature in the comment section. Though the answers are provided here, right? So you can check your answers by doing the question. And wherever you think there is a doubt, please pause the video and do watch that concept again, right? So that's all. Thank you so much. And whatever doubts you have, please put it in the comment section so that I can reply you all. So have a nice day. If you like the video, do hit the like button and do subscribe my channel to get the latest updated video. Have a nice day.